Good day to all viewers who are viewing this program. I am A. NAGARAJU, ME Structural Engineer. I am a retired engineer from Government Department, having vast experience both in field works and design works. I am going to present you a program that is designing of a roof slab, two-way slab. So two-way slab is something quite different from normal slab. So those things we will study while going through the program. We will go to the presentation now. Viewers, now we will go to the actual problem now. What is the problem given? Structural design of roof slab of a room following the provisions given in the IS 456. The dimensions of the room are 16 feet by 11 feet. Concrete to be used is M20 and the steel to be used FI 415. The width of support is given as 230 mm. The corners of the room are not held down. This is the problem. Now we will go into the problem now. First we have to collect what are all the details given in the problem which are to be used in our calculations. So Ly length they are given, width they are given as 3.35. Now we will find out Ly by Lx aspect ratio is 1.45, which is less than 2. Okay, why we are calculating it is that is LOLX less than 2. We have to check whether it is a one-way slab or two-way slab. Since it is less than 2, it is two-way slab. As the aspect ratio is less than 2, it is to be decided as a two-way slab. Then what are other things given? Weight of concrete 25 kN per m cubed. Composite strength of concrete M20, that is 20 N per mm square. Yield strength of steel 415 N per mm square. These are the things given. Now we have to go to the next step. Width of support is also given as 230 mm. Next, effective depth of the slab we have to find out, which plays a major role in calculating all other parameters. For this we have to refer note 2 for section 24 of IS 456. What is this? Here it is. Slab spanning in two directions. The shorter of the two spans should be used for all our calculations. For two-way slabs of shorter span up to 3.5 meter with mild steel reinforcement, the span to overall depth ratio given below may generally be adopted. Simply supported 35, continuous slab 40. Here it is a continuous slab. Why? So for Lx up to 3.5 meter of continuous slab, span to overall depth we have taken as 40 as given in the IS. And next is for FI 415 steel, the factor is to be multiplied by 0.8. So now it gives rise to 32. Modification factor assuming 0.5% steel from figure 4 in page 38 of IS 456. That is figure 4. I am assuming 0.05% steel. 0.5% steel, assuming this 240, it goes to 1.15. Now the L by D ratio calculated is 36.8. L by D ratio adopted is 25 only. Why? So it is only maximum. It is maximum. This is the maximum. So we can assume something less than that. So now I am assuming 25. Overall depth, span into 1000 divided by 25, that gives to 135 mm. Now I am adopting overall depth of 150 mm. From this we have to arrive at the effective depth. What is effective depth? That is the overall depth minus effective cover minus dia of rod. Effective depth provided is 150 minus 20 minus 10, 120 mm. This is the arrangement of slab S1, S2, S3. Let us consider slab S2. S2, you check the edge condition. This is spanning this way, continuous this way. S2 is continuous, this way S3. So it is a continuous slab. Continuous, this is also continuous. It is a continuous slab. Next step is edge condition. What is the edge condition? Two edges continuous, two edges discontinuous. So two adjacent edges discontinuous. That is the edge condition. Effective span, for which we have to arrive at Refer class 22B, page 35 of IS 456. Here they are given one condition. The general formula of clear span plus effective depth or center to center of support can be used if only the width of support is less than L by 12. This is the condition now. Yeah, continuous beam or slab. In the case of continuous beam or slab, if the width of the support is less than L by 12 of the clear span, the effective span shall be taken as given the 22.2. This is 22.2. So now what is happening we will see. What is L by 12? Here in our case it is 279.2 mm. Width of support given is 230 mm. So it is within the limitation. So width of support is less than 12, L by 12. Clear span plus effective depth is 3.5. Center to center of support is 3.58. Lesser of two values is 3.5 meter. Dead load we are assuming the overall depth is 150 mm, that is 0.15. So dead load is 0.15 to 25, that is 3.75 kN per meter square. Live load 3.5 kN per meter square. Flotation is 1.5 kN per meter square. Total load is 8.75. Next step is we have to find out the factor load, for which we have to find out the partial safety factor from figure table 18 of page 68 of IS 456. This is the table. Here the partial safety factor given is 1.5. So factor load is load into 1.5, that gives to 13.125 kN. Flexural design. Refer table 26 case 4 page 91 of IS 456. This is the table. Here Ly by Lx aspect ratio is 1.45, that is between 1.4 and 1.5. And our case is 4. Two adjacent edges discontinuous. We have to take the values for 1.4, 1.5 and interpolate. Ly by Lx 1.45. Now we will find out the bending moment coefficients. Negative bending moment coefficient is 0.071 for 1.4. 1.5 it is 0.075. Interpolating we get 0.073. The same way we have to find out the other bending moments. Alpha x positive, alpha y negative, alpha y positive. We have found out the coefficients for all the bending moments. Now we will find the actual bending moment now. Mux negative bending moment in x direction is substituting 0.073 already we have calculated into load into span square. So that gives to 11.74 kNm. Positive bending moment, that is 0.055 into load into span square, that gives to 8.76 kNm. Negative bending moment y direction 7.56. Negative bending moment, positive bending moment y direction 5.63 kNm. Check for effective depth. So already we have assumed some effective depth. We have arrived at the bending moment. Now we will check whether the effective depth we have provided satisfies the IS conditions for the bending moment calculated. Refer SP16 page 10 table C. This is the table. We are using high tension steel, that is Fi 415. So for the limiting moment coefficient is for 415 it is 0.138. So Mu is 0.138 FCK BD square. What is Mu? Mu we have already found out 11.74. So if we equate it, we will get effective depth as 65.2 mm. But what is the effective depth provided? 120 mm. So more than what is calculated. So we are adopting 120 mm as the effective depth. Reinforcement. Width of middle strip, that is 3/4 of Ly, and width of middle strip in the longer direction 3/4 of 4.88. So like that we have to calculate the strips, that is in two-way slab it is divided into segments. Edge strip, middle strip, like that. Now we have arrived at the middle strip. Edge strip also we can calculate, but that is not required for our calculations now. Mid-span movement along shorter span. 8.76 kNm already we have calculated. So this is the reinforcement formula, general formula for reinforcement. 0.5 FCK by Fi1 minus square root into 1 minus 4.6 mu divided by FCK BD square into BD, that is equal to AST. We will get the AST now after substituting the values. So now I am substituting all the values here. I am getting 214.172 mm square. We have to check whether it satisfies the minimum reinforcement condition. So minimum reinforcement, what is it? If we use mild steel, minimum reinforcement 0.15%, and if we use high strength steel, the minimum reinforcement should be 0.12%. Here we are using high strength steel of Fi415, so we are adopting 0.12%. For that, what is the minimum reinforcement? We are getting 180 mm square, but AST provided is 214.17 mm square. Diaphragm already we have assumed as 10 mm. Spacing of the rod now we have to calculate. So area of one rod into 1000 divided by AST, that gives to 367 mm center to center. But spacing should be limited to whatever is given in the IS. 26.2.1 48 of IS 456, it is 300 mm center to center, that is 3 times effective depth or 300 mm whichever is less. So here 300 mm is whichever is less, so we are adopting a spacing of 300 mm. For this 300 mm, what is the area of steel provided? Now it is 261.8 mm square. Now we have to find out the mid-span reinforcement along longer span, that is Y direction. So for which we have to find out the effective depth to be adopted. We have already found out effective depth as 120 mm. Now the reinforcement for the longer span should be below the reinforcement for the shorter span. The effective depth can be calculated by deducting the diameter of rod. So now it is 110 mm. Width of middle strip 3/4 of the LY. The reinforcement same way we have to find out the reinforcement for longer span. So substituting everything we get 159.02 mm square. Minimum reinforcement at 0.12% is 120 mm square. So spacing 367.7 mm per center to center, but it is not possible. Spacing restricted to 3 times the effective depth or 300 mm whichever is less. So that is 300 mm center to center. Maximum negative movement occurs in continuous edge in shorter span is 11.74 kNm. Effective depth we have already found out as 120 mm. AST required for this movement is 288.0 mm. We are assuming that half the AST from both the slab is to be bent up. That is from slab S1, S2, S3. From S2 we have to take the half of the reinforcement calculated to S1, in same way S2 also. So half the reinforcement is bent up. As the room dimensions are identical, it is taken that the same AST is required at the continuous edge of slab S1 also. Suppose in case the dimensions are different, again we have to calculate from the very beginning. Here what is the reinforcement? 285.09 is the reinforcement required, half the reinforcement from one slab and half reinforcement from the other slab. So what is the total reinforcement required is 285.09 mm square is required at the continuous edge. Area of alternate bars in longer span at support assuming similar room dimensions is 261.8 mm square. Already we have found out the value of steel. So half this way, half that way. If we take, it is 261.8 mm square. So additional reinforcement required at the to satisfy the negative bending moment at short span is 285.09 minus 261.8 mm square, that is 21.58 mm, 23.29 mm square. That is additional reinforcement we have to provide. Using 8 mm rods, spacing works out to 2156 mm center to center. It is not possible. So we have to arrive at use the minimum reinforcement, minimum spacing conditions of 300 mm center to center. Corners not held down. If it is not held down, it is likely that the corners will lift up, causing cracks in the slab. So to avoid this, torsional reinforcement is to be provided, for which we have to refer D1.8 page 90 of IS 456. What does it say? It is the reinforcement. The reinforcement should be 3/4 of the main reinforcement, and it should extend at each of these four layers will be 3/4 of the area required for the maximum and mid-span movement in the slab. So torsion reinforcement we have to calculate. Torsion reinforcement need not be provided at any corner continuously contained by edges over both of which the slab is continuous. So if the slab is continuous, that corners we need not provide any torsion reinforcement. Torsion reinforcement at corners, as given the D1.8 page 90 of IS 456, is 3/4 of LX. What is 3/4 of LX? It is 160.63 mm square. Size of square mesh is span by 5, that is LX by 5, that gives to 0.67 meter. Diameter rod proposed is 8 mm. So number of rods is 160.63 by area of 8 mm rod, that is 3.2. So number of rods provided is 4 numbers both ways. This is the general arrangement of the continuous two-way slab. This is given in SP 34. Bent up rods or continuous rods, like this. This is the general arrangement of rod. This is the torsion reinforcement mesh. Okay, this is the arrangement of rods. So thanks for viewing this video by A. NAGARAJU, BE, ME Structural Engineering. Contact number 9790731706, Coimbatore, Tamil Nadu. I have done this design in Excel spreadsheet, giving link for all the parameters and formulas. If anybody is interested to have this Excel file, they can contact me or by phone. Thank you very much for viewing this video.